To all those of you joining me for this video, thank you. I am Mr. Ish. We're looking here at a specific example. There are several sorts of these where limit x approaches infinity. We have a certain rational function. In this particular case, we have x divided by root of x squared plus 1. This is a classic example where the L'Hopital's rule will fail in terms of the limit determination. One would proceed with this specific rule application because when they would apply infinity in places of x, they would really end up with an infinity divided by infinity indeterminate limit form, for which they would feel the need to use that rule, and let's just abbreviate as LH. They would feel the need to do the rule. You would end up doing the derivative of the numerator and derivative of the denominator, and you can try it out and see exactly what happens. What will happen will not be much of a surprise, as you will find out when you do derivative of this x and you do the derivative of x squared plus 1, you're going to get 1 over here. Then you have to do the chain rule here, d over du, you have root u, and then du over dx, you have x squared plus 1. When you do this, derivative of this is 1 over 2 root u, and then you have a 2x coming from here. And then of course you could apply infinity in places of x after the derivative was completed. When you do this, you know the 2's will cancel out. You'll have x over root u. But when you flip this fraction, you'll have a root u over x, and the infinity can be applied. And you know when you resubstitute the u, which was x squared plus 1, look what you end up with. You end up with x squared plus 1 over x. And when you apply this infinity, you end up again with another indeterminate limit form, infinity divided by infinity. So then what happens is you proceed with yet another round of derivatives, except here things have flipped. You see how your original question was x divided by root x squared plus 1. Here things have flipped by the derivative procedure. Anyhow, you do the chain rule here. You'll get 1 over 2 root u, and you'll have a 2x. Here you'll just have a 1. When you do the cancellation of these 2's, you'll have x over root u over 1 with infinity application. That root u actually ends up becoming the denominator, and you know you could technically apply infinity. When you resubstitute the u, you end up with x over root x squared plus 1, and you're trying to apply the infinity, and then you end up with the same indeterminate limit form, except all that has happened is you've gone through the cycle and ended up nowhere. Everything is just flipping and it's flopping, and the L'Hopital's rule is not helping you out. So you have to understand and develop a second technique for solving a question of this form where x approaches infinity, and you just end up using this rule to no avail. Well, since the L'Hopital's rule has failed, we now have to come up with a fallback option, and the fallback option by no means is an inferior option. We can think about approximation using a good value. We can pick a good value such as 1 times 10 to the power of 9 or 1 billion. This value, when you would put here in places of x, what would you get? You would get 1 times 10 to the power of 9 divided by 1 times 10 to the power of 9 square plus 1. This plus 1 is negligible. You'd essentially, when you run it through the calculator, you'd get a 1, because you would end up with the same thing here in the numerator and the same thing here in the denominator. And this right here would be a bit of work because you're using an approximation value rather than using finesse. A better option here for some situation like this is to literally use some good finesse, where you're thinking of x divided by x squared plus 1, because you're looking at something at a very large value. In place of that very large value, 1 is meaningless, it's negligible. You're really looking at x divided by root of x squared, because plus 1 has no meaning in the face of infinity. Anyhow, then you're looking at x squared to the power of 1 over 2. You're looking at x over x, which is 1. And that 1 right there very well satisfies this. The answer for this specific limit as x approaches infinity is indeed equal to 1. You can use approximation, or you can use approximation with finesse, and this requires you to look at this 1 and remove it, simplify everything, and arrive at the value of 1. So this is a good classic case where the L'Hopital's rule fails, because if you keep employing it, you go through a cycle of never-ending derivative steps which get you nowhere, and then you have to resort to this option, which is not inferior by any means. It's an excellent option. Thank you for watching. Have a nice day.